All right, hello and welcome. Today is Tuesday, March 17th. If you're not on ClassFlow yet, go ahead and get on ClassFlow. Remember the password is, actually I'll type it out, QGX7X. So get on ClassFlow. Go ahead and tell us how you're doing. I'll go ahead and monitor. Can we please stream Minecraft? I don't have a Minecraft account and I don't intend to play Minecraft. We're gonna have to find a much better game if we're gonna stream video games. But anyway, all of that is after we learn our physics. All right. All right. So we have three people so far. Let's see, who are they? Oh, cool. Adam, Joshua, Owen. Very good. You guys are on top of things. Get with the program, guys. Waiting on a math web conference. Ooh, interesting. Doing web conferences. I'll give you my kid. Nah, it's alright. I don't know. It just looks really weird. The graphics are bad. Dalsa's having a Q&A right now. Oh, do they just randomly choose their times? I guess we're all like kind of doing our own thing, so there's no, there's no consistency. So you're gonna have to hopefully just use two different web tabs, I guess. But anyway, let's get going. Today we want to continue our discussion on circuits. Oh, by the way, make sure you hit the follow button, and that should let you type in the chat. And if you haven't done so already, make sure you subscribe to the YouTube channel. If you scroll down, you can see a link to YouTube. We need to get to 100 to get our own custom URL. So right now it's a bunch of code and I don't like it. So let's get to 100 so that we can have our custom URL. That'll be cool. So yeah, make sure you subscribe to YouTube down below. All right, starting with our PowerPoint, which is circuits number 1. We were looking at all these symbols. So we started with symbols, and we looked at the battery, the switch, the wire. Oh yeah, Dalton, I made it when I was like 9, please. I even have a rainbow dash. Okay. Alright, we'll leave the Minecraft for some other day. Perhaps after the AP test. We'll see. But anyway, I hope something better comes out by that. Okay. So we were looking at some... there we go. So we were looking at some symbols. So we did the resistor, the switch, the ideal wire. So any line that you see in your circuit diagram is just a wire which has basically 0 resistance. It's ideal. And we also looked at the battery. The other symbols that you will need to know is this arrow. So if you have a resistor with an arrow like this, the arrow tells you that it is a variable resistor. Okay? Which means that the value can be changed. Okay? We have one of them in our circuit kit. It's basically kind of like a combination lock or a dial that you can turn, and as you turn it, you change the resistance value of that resistor. So imagine a dial that you can connect. And as you turn this dial, you get different resistance values. Okay. What's happening is that on a microscopic or a zoomed in point of view, recall that the resistance equation R is equal to the resistivity of the material times L divided by cross-sectional area A. And you can imagine having a strip of a material, and one end of the strip is connected to the side, and then the second one, the variable part, which is this arrow, is a little prong or a probe, a metal probe that touches the material at different spots along its axis. Meaning, as you turn the dial, you're actually shifting this thing left and right. And so if you shift it to the right, like so, now the electrons, or the pseudo-positive charges that are coming in through one wire have to go through a longer path to get to the other end. Right? And so by traveling a longer path, you're basically increasing the L and therefore increasing the resistance value. Okay? Whereas if you had a shorter path, then you're off and you only had to crash into, only a little bit of rocks. Whereas if you take a longer path, you're going to have to crash into many, many rocks, and therefore slowing down the flow of current, slowing down how many charges you get per second. All right, so that's what a variable resistor is. And the last thing that you need to know are the symbols for the measuring device, the multimeter. A multimeter measures multiple things. You can set the multimeter to do volts, V, amps, A, and ohms, omega. Okay. Amps, which is your current, and ohms, which is your resistance. All right, so these things you can kind of put into your circuit diagram, and that'll show you that you've attached a measuring device. You've set it to voltage, then you're basically measuring the voltage across a certain region, and we'll get to that once we start building our circuits. Right? So here's a simple schematic. So a schematic is the diagram that you would draw for circuits. Okay, and this is the generic. Ooh, it looks kind of weird. Let me check. It's fine. The generic circuit diagram that has one battery, a pathway, and something to actually dissipate the energy. So as the electrons or positive charges fly out, it goes through this resistor. The resistor uses the energy and then converts it basically into heat. So here's our generic circuit diagram. Circuit diagram. Okay, so we have our battery, which is big line, small line. And remember, the big line is the positive, the small line is the negative. And then we need a connection. If there is no connection, if there's no wire or pathway for the charges to flow, then nothing flows and everything just stands still. So there has to be a closed loop. So here's our resistor. Okay. Now the battery doesn't actually give you the charges. It gives you a push. And that is very important to understand. Sometimes, there's some conceptual questions on the AP test, or your test whenever we take it. Is that, does the battery give you the charges that flow in the circuit? The answer is no. wires already have their charges. Again, they're pseudo-positive charges. In reality, remember, it's negative charges that are moving the other way. But the current flow diagram, current flows out of the plus end, okay, and then it'll continue its path. So this magenta color is I, which is the current flow of positive charges. And the I will continue to move forward until it gets to this resistor. It'll go through the resistor, of course, crashing and losing some of its energy. You can, if you want to do mechanics, you can imagine all these balls that are flying around eventually hit little rocks along the way, which takes away some of its kinetic energy. So similarly, the positive charges will lose some of its electrical potential energy. And energy is converted. So resistors convert electrical energy into thermal. And then back down, we keep going. We don't actually use up the charges. The charges still exist. Charges still exist. Charges are not used up. But now have less PEE. Electrical potential energy. Electrical potential energy. So similar to how a windmill or a fan works. Let's see, a windmill. Here's a windmill. Pew pew pew. Okay, so wind or air molecules eventually crash into the fan blade, which pushes the fan blade and makes it turn. But the air molecule isn't destroyed. It keeps, going, but now it has less kinetic energy. Due to the collision, it gave away some of its kinetic energy, forcing the, due to conservation of momentum, of course, the fan blade starts to turn. Okay. Similarly, the charges are still there, and they're on their way towards the negative side of the battery. Again, the battery didn't actually give you charges. Maybe one kind of pops out. Okay, one pops out, and this pushes the charges that are already there. This one here gets pushed forward, this one here gets pushed forward, and kind of like a conveyor belt or a conga line, it keeps pushing the next one forward, such that the one charge that was already here now gets a push, and it's pushed into. So whenever one comes out, there's another one that goes in on the other side. All right. So in order to make anything work, we have to have a closed circuit such that there's a pathway that leads us from the top end to the bottom end. Hey, charges have less P. Ha ha ha. They went to the bathroom. Good job, Owen. Good job. All right. So let's do a class flow real quick. Bam. Here's your question. Let's get on class flow. I'll stop. Ooh, we got some responses. I'm vibing, half asleep, sleepy, just fine, sleep. Why? It's literally 10 o'clock. Waiting on math web conference. Okay. Here we go. So we'll do multiple choice. A, B, C, or D. All right. If you're not on, hi, Mr. G, just dropping by to say hi and happy birthday, Charlene. Happy birthday, Charlene. All right, so get on class low and then punch it in. We only have 9 connections so far. So let's see. Megan, Darren, Adrian, Jennifer, Shiraz, Ryan, Joshua, Owen, Josue. Very good. You guys are Excellent. Leading the charge. Please sign into classflow.com/student. Classflow.com/student. And remember, it is QGX7X. Okay, so we're getting some answers. So this problem is showing you a battery, a closed connection. There's a resistor. Which of the following correctly labels arrows 1 and 2 and polarities? Polarity is another word for the potential, or the electric potential at that point on the battery. Essentially, is it positive polarity or negative polarity? Is it the cathode or the anode? Is it the positive side or the negative side? Yes, you got it. Leading the charge. These are the subtle physics memes you gotta pick up on. All right, we got 13 connections. Excellent. All right. All right, gonna close it soon in 10 seconds. Can I do countdowns, timers? How do I do that? Let's see. Cloudbot. Loyalty codes. Timers. Add timer. Name. Class flow timer. Times up. Interval. What is interval? Value in minutes. Oh God. How do I do 1/6? 0. Oh man, I have to do 1 minute. Okay, fine. Minimum amount of chat lines in the last 5 minutes required to activate the timer. Okay, this is way too hard. I don't understand. Let's see. Minimum amount of chat lines in the last 5 minutes required to activate. So you guys have to activate the timer. No, that doesn't make sense. I'll do my own timer. The old-fashioned way. 10, 9, 8, 7. Actually, everyone answered who's on, apparently. Only 13 of you. So, stop. The answer, apparently, most of you put C. Let's see. So, remember the big line is the positive end, so X has to be positive. The small line is Y. Y is negative. So X is positive, X is positive. So it's either A or C, and conventional current, and that's the current flow diagram we've been using. It's the movement of pseudo positive charges, and conventional current. Ooh, my bit rate is going down. Why? Conventional current is the flow of positive charges from the positive potential or high potential to low potential. The countdown doesn't work because of the delay. Yeah, you're right. So that's a very good point. So forget the countdown. I'll just say it. All right. So conventional current, or regular current, is the flow of positive charges goes from high potential to low potential from X to Y. Remember, there's a gap in the battery symbol. There's a spacing. That gap actually means something. That means that charges can't actually flow through it. It has to take the long way and go all the way around, the scenic route, if you will. It'll go all the way around to get to Y. So the direction of number one is conventional current. So therefore C is the correct answer. Yay! Woo. All right. Okay. Finally, Ohm's Law. I'll just move to one note. Ohm's Law is V equals IR. Ohm's Law. Here's a quick meme for you. Boom! Join the resistance. So that's what a real resistor looks like. All right. Ohm's Law, where we have V. Now this V is not the electric potential. Recall that V was electric potential, which is KQ over R. This V, even though we say it's V, is actually V with serif, which represents delta V, the difference in electric potential. And it's equal to I, the current, times R, the resistance. Thank you, thank you. It's a classic physics meme. V is equal to IR, so that means volts must be equal to amps times ohms, right? Because we also measure the change in potential with volts. So voltage, which is the change in potential, is I times R. Right. Okay. Now, a few things to note. Okay. Even though this equation, from now on, as we do circuits, it's safe to just write V equals IR. We already understand, I guess, from henceforth, we understand that V represents delta V, which is the change in potential. Change in potential. This is voltage, and so voltage is the change in potential. All right. Now, V is your source. So even though V equals IR, your source is the source. It doesn't depend on how much I is in the system. It doesn't depend what resistor you use in the system. It's just, this is a way to measure, if you know what I and R are, if you know what I, the current, and the resistor, or the total resistance in the system is, then you can calculate V, but it doesn't mean V is dependent on these two variables. So source, so independent, oops, I should write independent of the resistor. Okay. Resistance is also independent of your voltage. Okay. So R is independent, V is independent. The only thing that is dependent is the current, based on what voltage source you have, based on what resistor you have. I is what's going to change in your system, the amount of flow. Okay, if you have too much resistance, then the flow will decrease. If you have, very little resistance, the flow will increase. So current scales to make them proportional. Very good. Yes. So dependent on both. Both V and R. All right, back to here. Okay, let's do. Now, it seems like a BQ, but there are some conceptual things we have to understand about this. Right, in this problem, it says the circuit has a resistance of 100 ohms and the current is 0.05. But look at the circuit diagram carefully. What's at the bottom there? Chat, what's at the bottom? What is that drawbridge? A switch, yes. Very good. How's the delay? Is there like a... I'm using Streamlabs today instead of the regular OBS. I don't know what the delay is. Like 3 seconds? Okay. Well, I don't even know how to find that out. So if anyone knows how to change the delay on Streamlabs, please let me know and I will fix that. All right. So this switch, let's go and draw it. We have I don't like that. Battery. Now it doesn't actually matter where the resistor is, if it's right in front of the battery or later, because in our circuit diagram the wires are zero resistance, so it doesn't matter how far the charges have to travel. So there we have it, and then we have our switch. Okay, so this is like the axis of rotation down here, and it can rotate. Currently, when it's up, it is off. Okay, V is V, whatever V is. This is R, and it says R is about 100 ohms. Okay. Now, when it's in the off state, I know how to change OBS delay, but only for YouTube streaming. Not sure if, well, Twitch locks it unless you have beta access. Well, I mean, I was getting somewhere around 1 second yesterday with like regular OBS. But I think Streamlabs OBS does like slightly more. I'm sure there's like a setting somewhere, but I don't know where it is. All right, back to this. When the drawbridge is up, the switch is off, and when the switch is off, it means the current is 0. Okay, but V and R are still V and R. V and R are material properties based on what the source is and based on what the resistor is. So V is still V and R is still 100 in this example. Make sure you draw your omegas so that they look like omegas. Typically there's like a little thingy-mabobber, a serif, an accent. It goes all the way around. And then like that. Ooh, look at that omega. Alright. Bottom of settings, advanced. I'll do that later. But yes, please let me know or email it to me. I don't want to do it while it's live. Okay, so when it's off, the current is what turns off. And therefore, in order to actually have current, we have to drop this down so the circuit is complete. And now we have a closed path that leads us from one side of the battery to the other. Right? So this is where we, in class, we would all hold hands, make a human chain, and then make our own human circuit and make this little chicken thing that I have chirp. But unfortunately, holding hands is illegal for the next 2 months. Oh no, I crashed. Let's go back. There we go, we're back. So as long as there's a chain that connects from one side of the battery to the next, we have a working circuit. Ah, very good, Iovana. All right, so we have to close the switch first in order for it to work. And so, good. That's the trick. I is equal to, how much was it? 0.05 amps. So 0.05 amps. All right, so V equals IR is BO 0.05 times 100. All right, so 1/20th of 100. What's 1/20th of 100? 5. Very good. It's kind of messy. All right. Simple as that. Now, of course, you'll never get a question that simple. Remember the starting memes that I told you about? At the start of lecture, you get easy, and then when you actually do your mastering physics, yeah. Red. Wait, you did? Cool. With me? Wait, you graduated last year? Oh. All right. Anyway. So make sure your switch is closed. So look for these tricks. So if the switch is open, then the current should be 0. But obviously, based on the question that they're asking, we're going to assume that the switch was closed in order for it to work. The battery, again, is independent of the current. It's just if you know the current and you know the resistance, then you can solve for the battery, for the voltage. All right, light bulbs. 2 things that you need for a circuit. The light bulb is kind of like a resistor. A resistor gives you heat. Light bulbs are very thin wires, the traditional ones, where it gets so hot that it glows and gives you photons, light. And so this is basically a flashlight. If you can see the schematic, we have a switch up blank. There we go. We have a switch at the top. So here's our battery, and we have a switch up top, and then we have our light bulb. Light bulb. Here's our next symbol that you need to add to your list. You can just draw it as a squiggly, which is a resistor with a circle around it. So here's a light bulb. Okay. Now there is another way to do it, and that would be draw something like this. This is also a light bulb. Okay, but I prefer to just do the squiggly with a circle because it's faster and easier. So squiggly, circle, that's our light, and then we have to connect it. Okay, currently we don't have a closed loop, so the circuit is off. If this were a flashlight, you can imagine this circuit being inside of your flashlight. Okay. And you know how on flashlights there's this black little slider button? Or not a button, but a slider. Basically, when you slide it, what you're doing is pushing the drawbridge down. Pew, and this connects the circuit and allows the flashlight to work. Ooh, from mechanics to circuits to everything. All right, so the slider actually pushes it down, connecting your circuit. Okay, so what do we need for a circuit to work? Well, we need a closed loop and our energy source. That's all you need technically. All right. Even if you didn't have a light or a resistor to make heat, remember if you have electrical heaters, those electrical heaters are just giant resistors that are heating up as you send a bunch of current through it, right? If you have electric stoves, that's basically a resistor, and it does glow. You can see it because metals glow as they get hot. So based on the type of metal you have, the hotter they get, certain metals glow so much that they're super bright. Right? If you don't have a resistor, technically it is a closed circuit, but we call it a short circuit. No load, and a load is that in our PowerPoint? There it is. Oh, okay. So most circuits also have a load, a component that dissipates energy. So a resistor is a load, a light bulb is a load, something that will use up the electrical potential energy of your charge. Okay. But if you don't have a load, then the charges are just going to freely move from the plus side to the minus side. Notice how if I don't have a resistor in here, V is equal to IR, right? And therefore the current is equal to V divided by R, and V is whatever your battery is, but R is now going towards 0, and now you have V over 0, which gives you infinity. Oh no, infinite current. Yeah. So that would be bad. Usually infinity is bad everywhere if it exists in our universe. So anytime you meet infinity, you're not going to have a fun time. Now, is it really infinity? No. Technically, to save ourselves from infinite current, batteries actually have a tiny little resistor called internal resistance. Okay, so that everything can be dropped in front. Right. If you want to learn more about this internal resistance, consider taking AP Physics C next year. Unlimited power. No. So yes, it's going to be very high, and then the battery will get hot, and then it actually bulges up. And if you have regular batteries like Duracells and stuff, the flaps or the covering will come off, peel off. If it's a very high voltage power source, it'll actually blow up. These are called short circuits. They're dangerous. If you're PC or your computer dies at some point, it's probably because it developed a short circuit that shot, near infinite currents through it, melted stuff. When you have near infinite currents, it's so much current, so much charge per second, so much heat that it just melts things on its path. So you'll see things burn up and turn charcoal and stuff on your motherboard if you do develop a short circuit. Okay, so theoretically, if you get like hair or something, it is possible for hair to act as like a bypass for charges to flow, and it'll just go through it and short things. So keep your PCs clean them out, vacuum it. Clean your motherboards, kids. Yeah, try to use those CO2 canisters. They're pretty nice. And then what I do is I have my vacuum on with the upholstery cleaner, of course. But I also use a CO2 canister, so as I'm using the CO2 canister to blow the dust, the vacuum will suck the dust in. There you go. Bad for environment. What, the CO2? Well, I mean, first of all, in order to make those CO2 canisters, we sucked it out of the atmosphere anyway, so we're just returning it to the atmosphere, therefore setting everything into equilibrium. Thank you very much. Well, at least I'm using the vacuum to suck the dirty pollutants into my vacuum. All right, anyway, so short circuits are bad, so make sure you have a load, something that can take away your energy so things don't blow up, right? Oops, we'll just stop right there. Let's go and go to our Phet simulation. Phet simulation, and you can pull this up if you go to Phet. Go to physics, of course, and you'll notice that the physics stuff is at the top. Yay! So go to your Phet website, your favorite website. Under simulations, you'll see physics. I would think it would be alphabetical order. It looks like it: biology, chemistry, earth science, math. But of course, physics comes first. Yay! So click on physics, electricity and magnets, magnets, and circuits. We're going to use the Circuit Construction Kit DC. This one. I think I have it loaded. There we go. And this will allow you to make your own circuit. Unfortunately, we're supposed to use real things right now, but we're going to have to make do with our virtual environment. So let's go and make a circuit. Now, with this simulator, you can change it to like real pictures, or you can change it to schematic or diagram pictures. So here you go. So when I go to diagram pictures, we have diagrams or the schematic view. So let's have a battery. Boom. Here's our battery. So we'll make a simple circuit like the flashlight. Let's go and make the flashlight. So we have our battery. Let's attach some wire to it. Okay, and I can stretch it out like so. Let's go and put a switch at the top. Boom, there's our switch. Some more wire. Okay. And then over here, we will attach our light bulb. Okay. Now, this light bulb technically is in the form of an LED or something where you have if you take a look at LEDs, if you buy single LEDs, you'll notice that LEDs have a long tail and a short tail. The long tail is the positive end, and the short tail is the negative end. So you want to attach the long tail with the positive side of the battery. The difference between LEDs and regular light bulbs is that regular light bulbs regular light bulbs work both ways. Whether you connect it positive to positive or positive to negative doesn't really matter. You can actually send the current in reverse and it'll still light up. So regular light bulbs are just like resistors in that no matter which way the current flows, it'll still heat it up and therefore produce thermal energy If it heats up enough, it could even glow, giving you luminous energy, light energy, or photons. All right. So we'll go ahead and finish off our circuit. Notice how it's not closed. So we'll go from the bottom to there. And of course, close your circuit. Boom, there it is. And it's flowing. Whoa, look, we get light. Okay. Now, why are these blue things going from the positive side? From the negative side to the positive side. Can anyone tell us what is going on in this picture? Ooh, no, Sword Hero, go away. You're not in this class. Come back in like 20 minutes. Someone from AP1, look at these blue balls. They're going backwards from the negative side to the positive side. Bubble guy, salmon electrons. Very good. If you can take a look at the top right, you can see I have electrons on. So when it says show current, electrons. But I want to do this theoretical positive charger, or the conventional current. So here's our conventional current. And again, conventional current goes from the positive side to the negative side. Ooh. And so as it goes through the light, it heats up the wire that is inside the light, and then closes the connection. As you close the connection, the pathway is clear and it can go to the bottom of the battery. So similarly, if I don't close the connection, when I have the switch off, when the drawbridge is off, nothing flows, the light is off. All right, for those of you who are with us, go ahead and go to this, and instead of using multiple wires like I did, so let's go and delete everything, delete everything, delete everything. All right, delete everything. Okay, so I'm going to give you three things. This is what we actually do in class. So I give you one piece of wire. Now with the wire, you can stretch it out as much as you want, technically, but you only get one piece. You don't get a second piece. You get one piece of wire, one light bulb, and one battery. Okay, and your goal is to make the light bulb glow. So see if you can do that. I'm going to give you a minute or so. And then I'll open up ClassFlow. And what you want to do in ClassFlow is draw. I'm going to activate the drawing ability on ClassFlow. Go ahead and draw what you did to make this light bulb glow with just a single bulb, single battery, and single wire. So let me open up ClassFlow. Boom. So we will activate Creative. There we go. So now you should be able to draw. If you can't see the drawing the drawing menu, you might have to zoom out. So if you zoomed in too much into your screen, it might not show. So if you hit Control minus, this should zoom out, and then you should be able to draw on ClassFlow. Okay. Oops, I'm going to hide it so no one can see the answer. What you're doing is you're going on the Phet Simulation website, phet.colorado.edu, and you're going to play with the Circuit Construction Kit DC. Okay, and in this kit, you are to. Oh, that's Liam. Oh, get out of here, Liam. What review for the AP1? AP1? Oh, that is true. But we just did circuits, didn't we, in APC? So you should be all for it. So anyway, what we're doing is it's a challenge. It's the light bulb challenge. You get one battery, one light, and one wire, and your goal is to light up the light bulb. Right? This is actually a challenge. This is a challenge that MIT gave to some of their graduating students, and what happened was that essentially the MIT students could not do it. Well, not everyone, obviously. They cherry picked, and they made sure to pick the kids who couldn't do it. But MIT light bulb challenge.
The Massachusetts Institute of Technology.
We are the premier engineering and science institution in the world.
Woo, MIT! Oh,
Do you
can't
think
see
you
it.
light a bulb with a battery and wire? Do you think you could light a bulb with a battery and wire?
Yeah.
Light a bulb with a battery and a wire.
MIT student has to rephrase the question.
Yes,
Wait, you can't see it?
definitely.
Do you think you can light a bulb with a battery and a wire?
Here.
Battery and wire? Well, yes, why not?
Okay.
Definitely.
Okay, can you do that?
The interesting part about the batteries and bulbs question is that people always predict that they can do it. Students say, of course I can do this.
Any hints I should have here?
Teachers say, of course my students can do this.
Ow! Do you know why that didn't work?
I have no idea.
Battery could be dead, the bulb could be bad, I'm hooking it up totally incorrectly. I'm not an electrical engineer, I'm a mechanical engineer. But if I had to guess, I would say it's operator error.
Okay.
I know it's possible, but I don't know how to do it.
It's only after failing that you begin to get upset with the question and think, well, maybe it's a trick question, maybe this has something to do with manipulating the wires, they couldn't hold all the wires together.
You don't have a current if you only have one wire, you need to complete a closed circuit.
But that's not the case.
Oh, well, if I do it with a little light bulb, I just do this.
Ah.
In which case, the light just lights up.
It goes to the fundamental understanding of electricity. If one cannot light a light bulb with a battery and wire, then everything built upon those basic ideas has problems.
Cool. All right, so that's the MIT light bulb challenge. I think I can't remember, but the guy who was talking is from a different rival school, like Princeton or something like that. I can't remember. Of course, they cherry picked the videos of all the MIT kids who couldn't do it. That one girl didn't even complete the circuit. All right. So let's go back to our OneNote. And then let's see with class flow. Boom. Oh, we have so many drawings. Interesting. We'll stop it. Boom. Pause. And of course, what we need to understand is how the light bulb works, really. If you look at the picture here, the connecting points are not left and right, but they're, 90 degrees almost to each other. So here's what light bulbs look like, right? You have this bottom part that's rounded, okay, and then the bulb part. All right. So here's our metal. Now this metal wire, the wire itself, and then the resistor part. Technically, this is the light bulb part, but we're actually inside the light bulb. All right, so this one of the wires actually go all the way down and touch or makes connection with the base of the light bulb. What you'll notice is that there's a separation barrier at this black strip. Okay, this black strip kind of separates the external and the internal, or the bottom piece and the side piece. And so one of the wires is connected to the bottom of the light bulb, and the other wire, after going through the resistor part of the light bulb, is connected to the side part. So you'll notice that there are two metal portions on a light bulb. There's this upper metal portion and a lower metal portion. right? You can't draw. If you don't have the drawing tools, remember, if you hit Control minus, it should pop up. If you zoomed in too far, then the drawing tool doesn't show up. Yeah, I think Streamlabs. I mean, the Streamlabs things is good, but I got like the Streamlabs moderator thing. It's been working for like followers and stuff. So make sure you follow, and also subscribe to the. If you're just tuning in, subscribe to the YouTube channel. If you scroll down, I need to get 100 subscribers to get a custom URL for my YouTube channel. So let's hit that 100 as soon as possible. All right, so anyway, there are two metal portions, one at the bottom, one at the side. So that's why when you connect a light bulb, what you do is connect one end, the bottom piece, I guess, with the battery. We just use. So here's our battery. Okay, so that's the positive end, that's the minus end. And therefore just use the one piece of wire that you have to touch the side of the bulb to the bottom of the battery. Okay, and that's what the person at the end did to light the light bulb. I mean, I physically am unable to draw. Well, that is unfortunate. You should consider taking an art class instead. Isn't art like a requirement? Don't you have to take art to graduate or get your degree? Diploma. Allison Ann Leanne is asking a question. Hi, Mr. Z. I'm finishing up mastering physics, but I keep getting stuck on number 19. I've been recruiting to the help of Shibata and the other APC kids, but we can't get it. APC kids, you can't help Allison? Shame on you. All right, tell Allison to tune in to our Twitch stream to ask these questions, and then we can help. All right. Art history. Oh yeah, that counts, huh? Well, you see, this is what happens when you take easy classes to boost your GPA. You don't acquire the proper skill sets that you need to be successful in life. Oh, you just got destroyed. Comp-sci principles. Yeah. All right, so there's our light bulb challenge. We are good to go. Hey, look, it works. Wait, did it work? Oh, sorry. There it is. I forgot to put it up top. Yay, it's working. Yeah, it is. It's working. Oh, wait, what? What are you doing? No, don't do that. Is that from Streamlabs? Yeah, whatever. Okay, so how did you even do that? I don't even know. I thought that was a follower. Yeah, I didn't actually pay for Streamlabs, so I'm not actually using like their monthly subscription plan. This is just what is it? Just the basic features I assumed, which is the moderator feature, the pop-up. Okay. Well, I mean, I don't want to do it here, but if I start streaming like video games or something, then I guess I'll start. Oh, you set up your stream yesterday? Very cool. All right, we are almost at the end, so let's finish up here. Our next, what's our calendar? Energy, power, Ohm's Law, lab activity, blah blah blah. Okay, so the last thing we want to talk about is how we measure the brightness of a bulb, right? So one way to measure brightness is to measure the power output power drawn by the battery. Oh, sorry, by the light. Okay. Power P is equal to I times V. So we have V equals IR, VIR or VIR. That's Ohm's law. And here's the power equation, PIV. And PIV is, you know, let's see, P is power. Okay. You guys remember power from the work energy momentum unit, unit 5. AP1 students, what are the units for power? What are the units for power? Yes. Wait, who's Peterson? Wait, what? Is that Jacob's second account? That must be Jacob's second account. Yeah, power is measured in watts, capital W. Okay. Remember, capital W as a... Ooh, look at my moderator working. Streamlabs timed out. Why? Why? Are you trying to spam? Oh, doing links. Yeah, you can't do links. Anyway, capital W was work in your equation. As a unit, it's watts. Of course, I is in amps, and V, of course, your voltage is in volts V. Okay. Now, using your Ohm's law, you can actually derive other equations for power. Okay. So go ahead and substitute Ohm's law into your power equation. You get power is equal to I times V, which is IR. Therefore, it is also equal to I times I squared, times R. Okay. And what you can also do is solve for I from your Ohm's law equation. I is equal to voltage over the resistance, and then substitute this back into the power equation. So you get the third power equation. So power equals PIV, or P equals IV. Power equals I squared over R. No, I squared R. And by substituting V over R times V, you get power is V squared over R. All right, so memorize these three equations for power. You can use whichever you want based on what you have in your system or what is given in the problem. Power is a scalar, so you can just add up powers together. No matter what kind of system you have, no matter the circuit, add P values, P values like a scalar. Okay. This is capital P, not lowercase p. Not only that, there is no vector hat, so you should be able to remember that this is power and not momentum. Recall that momentum is lowercase p with a hat. All right. Okay, I will. You should be working on your mastering physics, so you can get started on the circuits one. There is a fourth mastering physics that is coming up, so make sure you're on top of it. Continue to work on your binders if you haven't done so. Make sure the binders are up to date. You want to be up to date on all those AP review questions and those tippers questions. All right, we'll go ahead and end the stream there. Thank you for tuning in. I'll see you next time.